These are the notes for chapter 21.1 through 21.3 on oxidation and reduction. Oxidation is known as, well, originally as when a substance reacts with oxygen, it goes through oxidation. It has actually been expanded to include any chemical change in which the oxidation number of an element increases. Oxidation number of an element increases. And then we have reduction. Again, originally was defined as when a substance loses oxygen, but now it is known as when an element decreases in oxidation number. So oxidation number decreases. Now what does this mean? Okay. Well, an oxidation number is known as its apparent charge. Now remember, an atom when it gets a charge is known as an ion, and so this is caused by an increase or decrease of electrons. So oxidation, you might see oxidation if your element goes from a 2 plus to a 3 plus. That is considered an increase in oxidation number. Or if it decreases, it might go from a -2 to a -1. That is a decrease. Or maybe 2 plus to a 1 plus. Well, this is an increase, sorry. So maybe a 3 minus. So if we wanted an increase in terms of negatives, you'd go -2 to a -1. You're getting more and more positive. That's going to be an increase, and here you're getting more and more negative, or going down, that is your decrease. So let's go back to oxidation numbers. There are some rules. Okay, first rule, if you have an element in an uncombined state, so it's all by itself, its oxidation number will be 0. For example, if you have Na, its oxidation number is 0. Okay, again, because it's just an atom. Maybe you see something like a diatomic element. Again, its oxidation number is still 0 because it's still just an element. Okay. These are uncombined. So it will have an oxidation state of 0. Then typically, if you have a monatomic ion, that's your second one, whatever its charge is its oxidation number. So monatomic, let me spell it right, ion. So if it says it's Mg2 plus, then its oxidation number is 2 plus. Okay. If it is Cl minus, then its oxidation number is a -1. Okay. Our third rule simply talks about hydrogen. Okay. In most compounds, hydrogen has an oxidation number of +1. There are very few exceptions. If you have what they call a hydride, and you'll know it by its name, like sodium hydride, then the oxidation number of hydrogen would be a -1. Okay. Oxygen is kind of similar. For oxygen, most of the time, in most compounds, oxygen would have an oxidation number of a -2. Okay. The only time it doesn't is when you have a peroxide. Oxygen would have an oxidation number of -1. Okay. Rule number 5. Rule number 5. Let's scoop this up just a little bit here. Sorry about that. All right. So with rule number 5, if you have a molecular compound, molecular compound. Again, we're going to talk just about binary. How do you know which one is going to be positive, which one's going to be negative? Because they're sharing electrons. Well, your more electronegative element is assigned the negative charge. Okay. And then last but not least, remember when you are doing oxidation numbers, because all compounds are neutral, when you add up all of your oxidation numbers, the sum should be 0. Again, 0 for neutral compounds. I should have specified that. Now, if they were asking you to find an oxidation number of, say, like a polyatomic ion, HCO3-, and they wanted to know what they were, in this case, when you are done, they should add up to -1. Right, so next we would have to practice. So let's say that we have phosphoric acid, H3PO4, and they ask you to assign oxidation numbers. You want to use your rules. Hydrogen should be a +1. It's not a hydride. How do I know it's not a hydride? If it was a hydride, it would be at the end. Like sodium hydride, again, bonded with a metal first, and then hydrogen would be at the end. So I know my H is a positive. And then you've got your oxygen. This is not a peroxide, so oxygen would be -2. So the one that I don't know is the phosphorus. Okay? So I have 3 of these. So total charge here would be 3. I have 4 of these. So total charge here would be a -8. Remember, this compound is neutral. And I have 1 phosphorus. So what is its charge? So you're going to do a simple algebra problem to figure out what that charge is going to be. So we've got x minus 5 equals 0. Therefore, x equals 5. So the oxidation number for phosphorus is a +5. Just takes a little bit of practice. Now, if we were to change this and let's say we looked at H3PO3, phosphorus acid, you're going to see a change here. Again, our hydrogen is a +1. We don't know our phosphorus. Our oxygen's a -2. Again, there are 3 of these, and there are 3 of these. So you've got 3 plus x minus 6 equals 0. So you get x minus 3 equals 0. Therefore, x equals a +3. So in this case, the phosphorus is a +3. So phosphorus is a +3, hydrogen is a +1, and oxygen is a -2. Now let's try one that actually has a charge to it so we can see the difference there. So S2O3 with a -2 charge. Here we've got two nonmetals. If you look at the location on the periodic table, oxygen is the more electronegative atom. Oxygen is 3, or -2, but we've got 3 of them. We don't know what sulfur is, but there are 2 of them. So that would be 2x. And in this case, this all has to be equivalent to a -2. So we're going to have 2x minus 6 equals -2. So that's going to give you 2x is equal to 4, a +4, because you're going to add 6 to both sides. So therefore x is a +2. So the oxidation number for sulfur is a +2, and the oxidation number for oxygen is a -2. Now let's look at the oxidation numbers in an actual reaction. Let's take a look at the reaction of magnesium with oxygen to produce magnesium oxide. Now it's balanced. All right. Magnesium, I'm just going to write the oxidation states over top of the elements. Magnesium here is an element, not combined with anything, so it has an oxidation state of 0. Oxygen, even though it's O2, it's still an element, so not combined with any other element, its oxidation state is 0. In this compound, we've got a metal and a nonmetal. Oxygen's most common is a -2, which is correct, which means magnesium would have to be a +2 in order to make that equal to 0. And then in a reaction, if this half is 0, then this half would have to be 0, and again a +2 and a -2 adds up to 0. So it works out perfectly. So these notes actually get us through 21.1 and 21.2, but we're running out of time, so I'm going to cut it here, and I will send out a video on identifying oxidation reduction reactions.